All right, students, I thought I'd make you kind of a solution set for this first exam. It's always helpful to go over an exam a second time and learn from your mistakes. So in this case, maybe kind of also self-grade it. But learning from your mistakes is good. We need all this material going forward. And so even though you might have missed the points now on this exam, let's not do it again because these things build on each other. And so this will help you as you go to exam number 2, exam number 3, and then also on the final exam where you see, these same topics again. All right, so I'll do number 1 here first. This one is straight from chapter 1, unit conversion. It says, what is 854 centimeters in feet? All right, well, maybe I'll have enough room to kind of doodle here, but my point was look at what units you have and put that on the bottom and put in top what you want to convert it to. Now, ultimately, I want feet. So the information that's given is how to convert centimeters into inches. So let's get rid of inches and put feet. And so 1 foot is 12 inches. So grabbing a calculator, this 854 divided by 254, and that also divided by 12 is 28.0. And so C would be the answer here. All right, going on to the next one then. It says, when a projectile is traveling through the air, the acceleration in the horizontal direction is 0. So hopefully you nailed that one. That was our ongoing discussion about projectile motion, that you just, I don't want to say it, the vertical acceleration. I guess that would be the tempting mistake to say something about the vertical one, but it's asking about the horizontal one, which is 0. All right. A ball is thrown straight upward. At its highest point, its acceleration is... And I guess the short answer is the acceleration is always 9.8 meters per second downward. Always, 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 always. Never anything different. However, it's easy to kind of lose your thought and think about the velocity and go for A. The velocity is 0, okay? And, of course, don't confuse those two, but it is quite possible. Okay. Rock is dropped from rest, ignoring air resistance. How far does it fall? This is kind of a straight plug and chug type of equation into our kinematics equation. And this is just one-dimensional. And so if we say that it started at rest, that's 0. I guess if we move it to the other side, that will be the distance it moves. This then would be this 1/2. And then we can put a 9.8. Oh, sorry, I forgot my time squared. And then 1.25 squared. And so this would be 1/2 times 9.8 times 1.25 squared. And looks like right here is the closest answer there. And so C for number 4 here. All right. Moving on down to this next question. The units used to measure acceleration are, and of course, maybe the best way to say it verbally is it's a change in meters per second each second, which, when you flip and multiply, becomes meters per second squared. So it would be D. Which statement is not one of Newton's 3 laws, and it looks like C would be that one. C is a true statement. Free-falling objects have a downward acceleration of negative 9.8 meters per second squared. Yes, that is true. However, it is not one of Newton's 3 laws. So I guess that would be the correct answer here. Number 7, an object starts at rest and has an acceleration that changes with time given by this formula. How far does it travel during from 0 to 4 seconds? All right, so here's a little calculus one here, and as we mentioned, you can get to velocity by taking the antiderivative of the acceleration. So if we put in a 3t dt, we would get the 3 as a constant and then a t squared over 2. And then you might argue that there'd be a constant of this integration. But we can also interpret that as the initial velocity as we kind of read the equation here. Then we can also read in the sentence it says an object starts at rest, so we give it a 0. So we'll call that one nothing to worry about there. Now to get position, that is the antiderivative of the velocity. So the velocity is this formula, 3t squared over 2 dt. So if we pull our constants out in front, the times squared becomes times cubed over 3, and I suppose you might even say plus a constant, which, if you interpret, would be the initial position. And since the question says how far, I can move it to the other side and say final minus initial. That's what they're after. And then over here, the 3's can cancel off, and it looks like I have 1/2 t cubed. Actually, I suppose another alternative is just to put limits here of 0 to 4, and then you wouldn't need a constant. But in either case, you're going to have a 1/2, and you're going to have your time, which is a 4 raised to a power of 3. So 4 times 4 is 16, times 4 again is 64. Half of that makes 32. So that one might be a little bit more of a challenge because of it having the calculus in it here. All right, next page. So this next page here, number 12, says that we have a 12.2 kilogram block, slides across the table with a horizontal force of 25.2. The frictional force is 12.0. What is the coefficient of friction? All right, so maybe kind of a side picture to get a good physical idea of what's going on. Maybe I'll make a little table, put a block. But the way this is described then is I have an upward normal force, I have gravity down, mg, and I've got a horizontal force, slides across with a horizontal force of 25.2, slides across the table with a horizontal force. The frictional force is. And so they list the frictional force, and now that I did all that, I kind of realized that's more than needs to be done for this problem. That's more for the free response. Because the frictional force is the coefficient times the normal. And the frictional force is just straight up given. Okay. And the normal force, you don't really need to write the horizontal forces to figure out the up and down forces. And so the up and down got to come out to be 0. So the upward normal has to be the same as the gravitation. And so this is just the weight of the object, mg. So the coefficient would be that 12 divided by mg. That's what this one boils down to. So 12 divided by an m, which is 12.2, and also the g, which is 9.8, is a 0.1. So looks like A would be the correct answer for number, what is this, number 8. Okay, good. And it kind of looks like we're getting into the harder ones of the multiple choice. Ah, yes, here, a ball has a radius of this amount, and a mass of this amount, what is its terminal speed? Well, this is our discussion in Chapter 5. This might be the hard one here in this multiple choice. It's getting pulled down by mg, and it's getting lifted up by this drag force. And the drag force depends upon, there's that factor of 1/2. The c is for the shape of the object. Rho is the density of it. A is the cross-sectional area. And then v squared is its velocity. And terminal speed is reached when these two match. And so it starts off with no drag, and then it gets bigger, bigger, bigger. Eventually, it equals its weight. So when this number here is at terminal speed, it's equal to its weight. And, of course, in this particular problem, let me give myself a sheet of paper here maybe to work on. But you probably could just see that in your notes that we had this little formula. Bring the 2 over here, 2mg, then divided by the drag coefficient, then the rho, then the area. That would be the terminal speed squared. So if we just plug everything into here and then take the square roots, we will get the terminal speed. Okay, so let me put those in. All right, so here's the calculator. Actually, maybe we should talk a little bit about these separately before we try to put them in. The mass we are given, however, we're given it in grams. So know that I'm going to do everything in those units of kilogram, meters, and seconds squared. So that 145 grams I'm going to put in as kilograms. The G, well, that's the standard 9.8, and it's already in meters and seconds. So that one's good. These other ones might be a little bit of a challenge. The C, you got to go to that table, and that's maybe the key to this problem is to say, okay, well, where do I get these things? And so the drag coefficient is, I guess, in table 2 there. And since it says it's a baseball, we can look at the sphere and get 0.45. Pretty sure that's right. Might want to look that one up. The density is one we've done a couple of times, but again, it's right there in the book, and it says we're moving through air, and so this is the density of air, 1.21. And maybe the cross-sectional area is the kind of the hardest one, but if you kind of draw a sphere, there's this baseball falling. The cross-sectional area is kind of this disc, if you will, as it's falling down. I mean, I know the whole object is a sphere, and so I guess I'm trying to say a round object, then kind of the shadow of it as it falls, something like this, is a circle. And so this would be pi r squared. And they give us the radius. But again, little warning here, they give us the radius in centimeters. So we're going to want to make sure we watch our units here and put it in meters. Okay. So this one's about this drag coefficients and the terminal speed and a little bit of unit stuff in here. So this is I think the tough one here. All right, so let's put all this in. So this would be 2 times G, 0.145, times the mass times G. Then divided by the coefficient, the drag coefficients of a spherical object, the density, the pi, and then the radius squared, 0.0365 squared. And so that would be the terminal speed squared. So one last step, taking the square root gives me at 35.3, And so D would be the answer to that one. All right, one more multiple choice one. Here, a 4-kilogram object is pushed to the right this much and to the left by this much. All right, so maybe I'll draw a little picture. 12.2 that way, a picture that way, 14.4. If there are no other forces, okay, so I'll pause there. No other forces means the net force would be combining these two. So 14.4 minus, keep their opposite directions, 12.2 leaves me with 2.2. And what is the magnitude of the acceleration? So this is the net force. And if you divide that by mass, you get acceleration. All right, at least magnitude of it. The direction would be in the direction of the 14, which is to the left. We don't really need that piece of it. So let's go to the 2.2 divided by its 4, coming up with 0.55. So the last multiple choice one here would be A. All right, now for the meat of the test, if you will. Looks like we have a projectile and a one-dimensional motion, and then again, the harder one with some friction. Doesn't have the hard drag coefficient one, but it does have the coefficient of friction again here. So let me grab my yellow sheet here, and let me just go ahead and say, all right, let's look at the first problem in number 11. And it says a baseball is hit. So I'll take a little baseball. I'll hit it. It's going to fly through the air. It looks like it gets caught a little bit higher. We can call this the launch point at 30 centimeters. As a baseball is hit 30 centimeters above the ground at an angle of 60 degrees above the horizontal. It is then caught 83.8 meters away horizontally and 2 meters above the ground. What was the initial speed of the hit baseball? All right, so as you have seen me do, I hope you've seen me do, I'll do it yet one more time. Divide your paper into X and Y motion and write out your equations of position. So I'll put it down for the X, and I will also put it down here for the Y. And hopefully by this point you're getting pretty good at saying, well, where am I going to put the origin? And you've got some options here. You could put it where the ball gets launched. That's always a good one. You could also put it for this one right below where it gets launched. And since things are measured from the ground, I guess I kind of gravitate towards that one. So I'll go ahead and do that, because then if we talk about the ball launching out to here, we could see it ends at a position of 83.8 meters, but it starts at a position of 0. And its initial speed in the horizontal direction would be whatever its initial speed is, but cosine of 60 degrees. And then 0 acceleration in the horizontal direction. And so if I put in what I do know here, the 83.8, and then the cosine of 60 is 1/2 V naught T, I would get what I'd call my first equation. Doing the same logic here for the Y, it's going to finish at a height of 2. It's going to start at a height of 0.3, and so there is a little bit of unit conversion in this one, so be careful there, 0.3. The initial speed in the vertical direction would be V naught sine of 60 degrees. And 1/2 the acceleration would be the negative 4.9 T squared. And I would expect you to kind of get out your calculator for the sine of 60. But so that's that root 3 over 2. And if I move this over to here, I get a plus 1.7. That kind of makes sense. It was caught or finished at a higher spot than it was hit. This then would be the 0.866 V naught t minus 4.9 t squared. All right. And then that I will call my second equation. And now the math begins. Solve one of these and put it into the other. And maybe since we are after final speed, why don't we solve this first one for time? So 2 times 83.8 divided by V naught. And then put that into here. That way we'll have an equation that doesn't have time in it and only has initial velocity, and then that's what we're asked for. I guess if we did it the other way and solve this for initial velocity and put it into here, we would have an equation that has time, and we could solve it for time. But then we would have to go back and put that into either that equation or that equation to get the initial speed. And that's okay, too. It just may be an extra step longer than necessary. So I'm going to solve it for time and put it into here. So 1.7 equals 0.866. I'll put a V naught. And then put in the time, which is 2 times 83.8 over V naught. And that's what's nice about that one, is the V naughts will cancel off. And then 4.9, and then, again, this squared would make a 2 squared here, and looks like an 83.8 squared here, so that squared over V naught squared. And then, why don't I work out some numbers here? Maybe starting with this number here, since it's already in my calculator, I'll go times, and then times a 2, and then times an 83.8. So this number is 145. Now, if I were to move it to the other side, it would become negative. So why don't I go times -1? And then I would add that to this 1.7. All right, so this number moved over to the other side gives me a negative 143.4. Together with, and I'll just put the negative and the V naught squared here, but I got a bunch of numbers, so I'll go 4.9, 2 squared is a 4, 83.8 squared equals, and so this is a 137,600, and I'll just call it 40. And then finally, to solve for V naught, first cancel a negative on each side, and in my mind, imagine me moving this over to here. So that'll put V naught squared upstairs. And then imagine moving this over to here. So I'll have the numerator divided by that one. So I already have the numerator, so now let me divide it by the 143.4. And the last step then is to take the square roots of all of that, and to 3 significant figures is 31.0 meters per second. And I guess we can debate a little bit on the significant figures. It looks like there's 3 there, there's 3 there, there's 3 there, 3 there. And I only used 9.8, but in our area it's 9.80, so maybe I really did use 3 there. So that gives me an answer of 3. Anyways, there's the best answer for this one. And it looks like I'm out of yellow paper, at least for a moment here. Let me grab a new pad here. Okay, so grabbing a new pad, let's go to the second free response question. This one says, during a car race, the winning car starts from rest, accelerates at 4.5 meters per second squared for 400 meters, okay, to get some maximum speed. Doesn't say what it is. Then the car travels at this maximum speed for 12 seconds, okay. And then finally, the car slows to a stop while traveling another 500 meters. What is the total distance traveled? So it looks like there is 3 parts to this problem. And this means that the 3 individual parts each have a constant acceleration. So I can use those constant acceleration kinematics equations. But I got to do it separately. I cannot do it in one big shot. So if I call this, say, D1 and D2 and D3, my goal is to find the sum of those. Now, maybe I should go back to constant acceleration because they told me in the first part the acceleration was 4.5 meters per second squared. Now, in the second part, they did not explicitly say it, but they did say the car travels at this maximum speed for 12 seconds. So in other words, it doesn't go faster, doesn't go slower, doesn't turn, it doesn't have an acceleration. The acceleration is 0. So they did tell me the acceleration indirectly. Now, the last part, they didn't tell it to me at all, although they gave me enough information that I could figure it out. But I'm going to just say, do I really even need it? Because if my goal is to find the total distance traveled, you'll notice that they really helped me out in this problem. They already gave this number as 400 meters and this one as 500 meters. And so really this problem boils down to what's the distance traveled during these 12 seconds. And maybe I'll put right here, time is equal to 12 seconds. So this is going to be a 400 plus however distance they travel during the second leg of this, and then they slow down. So I don't really think I need any kind of acceleration or any kind of time or anything calculated for this one. That's just a waste of time and unnecessary. What I need is the distance traveled in number 2. And if I write down that second kinematic equation, I will see that it's kind of an easy piece that I need too, because this one goes away. There's no acceleration. And if I just want to know how far it traveled, I'd go x minus x naught. That's just the initial speed multiplied by time. You might even call it initial speed, final speed, middle speed, because it always has this speed. Okay. And I know the 12 seconds. So this is what it boils down to. Now, there is a little bit of work I need to do on this problem, because to get the initial speed in the second part, that would be the final speed in the first part. All right. And so as I think about my kinematic equations on how to get that speed, my first thought maybe goes right here, but that involves time. And also the first kinematic equation involves time. And that's what I'm not given. I'm given distance and acceleration. That sounds like a perfect recipe for the third kinematic equations. But I will say it again, doesn't matter which of the kinematic equations you use, you can get there. It'll just take more than one step. This is the one you need to get there in one step. All right, so to figure out the speed in one step, I'm going to look at part 1 and say, okay, now part 1, they said it started at rest and had an acceleration of 4.5, and it did that for 400 meters. So the finishing speed in part 1 would just simply be 2 times 4.5 times 400, and taking the square root, oh, that was a good one because that's just going to be an even 60. To perfect square. And so now I can use it back up here to say it's 60 meters per second for 12 seconds. So if I take that speed and multiply by 12, I am at 720 meters. So this middle distance is 720 meters. So finally then, adding the original distance during acceleration of 400 and the original, or the final slowing down of 500 meters, we get a total of 1620 meters. Yay! Okay, so there's number 2. Hopefully that will help any confusion and make you that much stronger for the next test. And there will be many tests, not just tests in this class, and not just other classes, but the tests of life. So we'll keep plugging through and be resilient about it. All right, so here is number, I guess, 13 on my little sheet, but it would be the third one and number 11 on Canvas. But it says that we have a 5-kilogram block is sliding at a constant velocity across a level table with friction between the table and the block. Now, they even give us a hint. This should tell you something about the acceleration. So, like all these problems involving forces, let's try to get a step 1, a good physical picture of what's going on. So I'm going to doodle a little table. I'm going to put a block up here. And I'm going to say, here it is moving across the table. And I'll just say it's moving. And it's hard to see in this picture. My picture kind of looks like it's moving in the X direction. And because it's kind of hard to see that, maybe I'll just call this a side view. Maybe not to be confused with looking down from the top. So looking down from the top, I might have a table here. And maybe if I call the dimensions of the table the grid, so along the long part of the table will be X, and along the short part will be Y. If that's the case, then as we go on to read this, it says that there are 2 horizontal forces pushing on the block. The first one is to the east. All right, so let's kind of just, since I already kind of put a grid, let's just pretend the table is labeled out as we traditionally do. The x-axis is east. So that means the negative x-axis is west. That means the y-axis is north, and the negative y-axis is south. So if this top view, this is my box, they're saying that I have one force, I'll label it in green. So there are 2 horizontal forces pushing on the block. The first one is 15 east. So it's directly along the x-axis. Okay. The second force might be the harder one because it is a value of 12 newtons, but it is 40 degrees north of east. So it's kind of angled like this. It has a value of 12, but it's 40 degrees to the north of due east. North of east. Okay. And then the problem goes on to say, what is the coefficient of kinetic friction? And so I took some extra time purposely, not just because this is the hardest of the problems, but because, again, getting a picture of what's going on can be a little misleading if you're just kind of drawing it on a piece of paper. Because, see, I started to draw and say, hey, the block is moving this way, but from a side view like this, it doesn't really show that it's moving kind of at an angle along the table. And that's this part that I'm really trying to emphasize. You really need to have a good physical picture of this one. Because without a good physical picture, you're not going to do the free body diagram right, which means you're not going to add up the forces right, which means you're not going to get the answer completely right if you don't have a good physical picture of this. See, I say all that because when I go to a free body diagram and I say, what forces are on here? Well, I'm hoping they're kind of obvious. My answer to you was always weight and everything touching it. So if I start with weight, in this picture, it would be pushing down mg, and it's a little harder to see than in this picture because down is into the table. So when you're doing a top view, it's kind of hard in this, two-dimensional piece of paper to draw down. That's why the side view is nice. But the side view is not very good because I really can't see the block moving at an angle. And so maybe the best thing to do is take an object. I'll take my eraser and say, look, this sheet of paper will be the picture here. And so if I turn it the long way, I guess. So to the right is the east, so it's getting pulled to the east, and it's also getting pulled up a little bit. So the motion's probably something like this along the table. But what's absolutely crucial here is which way is down, and that's this way. Down is not, in this picture you can see down, but you might be tempted to say down is kind of this way in the picture, south, and south is not down. Just like in this picture, up is north. Sorry, up on the piece of paper is north, but that's not up. Over in this picture, then the normal force would be here. And here's what I'm getting at. I'll say it again. It could be really easy to mix up the 6 directions. You have north, you have east, you have south, you have west, you have up, you have down. And north is not up. Sometimes when students get this confused, I say, look, do me a favor. Put this on the table. Okay, now I want you to point which way is up. So for you guys on the camera, I'll just use my thumb. I'll say, well, the camera's up above, and so that's up. Okay, fine, that's up. Now, point to which way is north. Okay, well, the mountains are north. Yeah, so in my room right now, the north is that way. So that's north, that's up. See, they're not the same direction. North is not up. South is that way, and down is that way. Down is not south. So, again, without a good physical picture, you could really head down the wrong road and start labeling up and north as the same direction. And they're not. And that will get you down the wrong road just because you got the wrong physical picture to begin with. So this one's easy to do that. And so I'm spending a lot of time here trying to make sure that you see the difference between up and north, east and west, south and down. Okay, so those are our 6 directions. You see, because this problem asks for the coefficient of friction, maybe the first thing I would do is to say, all right, the frictional force is equal to the coefficient of friction times the normal. And so my goal then would be to get both the frictional force and the normal force. And that's why I got to picture the 6 directions, because when I look at this side view right away, this up and down, which I could say add up all the forces in the up down direction. So normal force would be up, gravity, that's its weight, would be down. It does not accelerate up or down, so I'd put a 0 right there. So the normal force is mg. And putting in the 5 and the 9.8 comes out to be 49 newtons. So that's one of the pieces I need. And that might be the easier one, as long as you saw a good physical picture. Now, the hard one comes in right here as what is the frictional force. And that's where this kind of this top-down view might be nice. Let me do the free body diagram in this top view. I'll just take this little rounded object to, or a rounded dot to represent my object. And then as I'm looking down, I'll do a grid where this is north and this is east and this is south and this is west. And then that way, when I draw my two forces, I can draw this one completely east, which is 15. And if I draw them head to tail, I can draw this one that has a length of 12 and an angle of 40. So when I take my piece of paper and cut it into X and Y, and say, let's add up all the forces in the X direction, and let's add up all the forces in the Y direction, setting each of them equal to mass times acceleration, I can probably quickly just say, okay, those come out to be 0. And so then, as I kind of look at this, noting that it is, heading off in some kind of XY direction, when I add up the forces in the X, I would have the 15 plus the 12 cosine 40, and then the friction. Oh, and I apologize. I did not put friction in my free body diagram. I focused way too much attention up here on direction and the other forces. And so let me go back to say, okay, now remember, it's the force of gravity and everything touching it. So force of gravity was mg. Everything touching it was the normal force, and then I didn't put here the friction. And in this picture, the friction would be at some kind of angle, not real sure what angle. I guess I could figure it out from here, but there'd be some kind of friction that opposes the sum of these two. So I could argue that the force of friction would just be equal to the net force of these two. So I just got to add up these and figure it out and say the magnitude of these two is the friction. And so I'll put that in here. Maybe for starters, I'll just say it's minus the friction in the X direction, and that has to equal 0. And then over here, I would come and say, okay, well, what forces do I have in the Y direction? And this is the only thing I have in the Y direction, the 12 cosine 40 degrees. And then minus the friction in the Y direction. And so keep in mind, I'm trying to find this friction in the Y direction. And so, I'm sorry, total. And I have now the friction in each of their corresponding directions. I'll just get a number here. This would be 12 times the sine. My bad. So cosine, sine. Okay, so this would be 12 times sine of 40. And so this would be 7.71 newtons. And this over here would be 15 plus 12 times cosine of 40. And so this would be 24.2. So it kind of makes sense. I'll say it again. We should have then most of the friction in the negative x direction and a little bit in the negative y direction to oppose the two horizontal forces. The big thing is just don't confuse up with north. All right, so finally, to figure out the frictional force, I will take the x component of the frictional force and the y component of the frictional force. I will then add those together and take its square root. So I will take my answer, which is the x component, and square it. The y component is up here. Let me just copy and paste it and square it. Let me hit enter. Let me then hit the square root, and I come up with a frictional force that is 25.4. And that's, like I said, the big pieces of work. And I'll say it again, if you were to confuse the up with the north, you might mix. I mean, you'd get something different because you would mix it. And easy to do. Which is why I like to give partial credit here, because I can then take a good look and say, okay, their logic is sound. They're doing all the pieces right, but they made this small mistake at the beginning of not getting a good physical picture. So there are many problems where I've seen that this just looks totally wrong. All these numbers just don't make sense, but it really is not that significant of a problem if that's the only mistake you made. All right, so let's finally finish it up and say, all right, how am I going to get the coefficient? So the coefficient is the frictional force over the normal. And now that we just did the frictional force of 25.4, and we did the normal earlier on at 49, we can then say, take that number, divide by 49, and get a 0.5. And I guess we can debate how many significant figures are here. Each units are each Newton, so there's no units for the coefficient. And 3, 3, 3. And if I think of 9.8 as 9.803. All right, so maybe that's the correct number of significant figures. All right, long problem, that last one. Good problem. Hope you did it all right. And if not, maybe you just made one little mistake, but I could follow your logic, and hopefully you still got significant amount of partial credit. Take care.